one, who's my closest colleague for 4 years. And we did many interesting things together. And I will be presenting also some of the work I did with him and some continuation. Anyway, so if you have any questions also online, I will try to keep an eye on your questions. Since we don't hear you online, you can just try to write it to the chat, and I think somebody will be checking up the chat, and then just ask me anytime. Okay, so so the motivation for studying social systems in terms of physics is there are several reasons for that. So first one is that what we think is that so typically modeling social systems is very complicated and complex task, and there are many models that attempt on understanding the social systems, agent-based models, for example. Why we use the methods of statistical physics in order to try to understand the behavior is that we think that the advantage is that it doesn't give you maybe the most precise model or the best model for the let's say prediction, but it allows you to somehow understand the general picture of the system. So it means it allows you to understand what happens if this parameter changes or that parameter changes, whether the system undergoes like a phase transition or whether there is like continuous transition from one state to the other. And this was basically our main motivation of using statistical physics and application and the results that we've been working in statistical physics to study social physics. I will make an initial remark in the sense that I've been talking to several people from sociology and psychology, and very often they say this is all nice, that what you do, but it's too simplistic, and we don't think you can model the complex social systems with just imagining that the particles are the people are just spins, and they basically change their behavior, and you just use your methods and use your equilibrium free energy to describe the full system. And the truth is that we acknowledge this. So if you want to study the exact evolution of these systems, then you would probably want to opt for another model. However, we think that since the social systems are really complex and complicated systems, the first aim is maybe in order to really be able to model the systems, it's not to start from the most precise model, but to understand what's going on in the sense that qualitatively, we would like to understand what are the possible outcomes, what are the possible phases, macroscopic phases of the systems. Is the society polarized, or is it fragmented, or is it cohesive, or what happens with the society, and whether these macroscopic phases occur abruptly, or whether there is like some slow change, or what happens. And we think that once we understand this behavior, then we can make use of it to really create the nice, precise models of societies. And now I'm mentioning it because it's kind of often misinterpreted in the sense that now the statistical physicists want to describe yet another system, and they will claim that their approach supersedes or like is better than the other approaches. I think this is also we've been guilty of that, the common misconception. So of course, if you are modeling physical system, natural systems, then these systems typically have many symmetries, which means that you can make use of these symmetries and really try to solve the system in the sense that you will know exactly the behavior, you will know the phases, you will know the evolution, etc., etc. But of course, we are aware that this is not the case for social systems. People are different, the connections are not homogeneous, etc., etc. So this means that you are not able to describe the whole society by one or two parameters, for sure. But what we think is that it is useful still to use these approximations to understand the general behavior of the system. Because if you look at a society, it just seems as a complete mess and really complicated behavior. And when you try to study this without any prior knowledge, it's really complicated. So what we hope for is that our approaches may help to understand the general behavior, and then as a second step, you might want to use some of these properties, not even the models, but maybe the properties or like the phenomena that you observe to describe the social system. So this is just before I start to address this common comment by sociologists, which is of course relevant. Good. So I start with just a brief overview of some of the well-known models of sociophysics. So maybe the most known, the best known is the voucher model, where the agents influence each other and they change their opinions. And this has been studied for many decades. And this is very important model. Or then the second model that I mentioned is the Schneid model, where it's based on the social validation. United we stand, divided we fall is the saying, where the idea is that you get the validation if by the friends, and interestingly enough, you can observe a phenomenon that the two equilibrium distributions are either ferromagnetic or antiferromagnetic distributions, which is something that you don't observe normally in statistical physics. And then you have Axelrod model, where you have the dissemination, bounded confidence models based on the opinion adjustment for the opinions if they are sufficiently close. So all of these models were motivation for our models, and we try to use them and take an inspiration from them. But what we use mainly are the two main driving mechanisms, so to say. So the first one is the mechanism of homophily, where we say people are trying to hang out with other people with similar opinions. So basically, if you imagine a person having binary opinions, for simplicity, one can generalize it to continuous opinions, etc. But for simplicity, let's say you have several binary opinions. So if the people have many different opinions, they then tend to not be friends with each other. If they have many similar opinions, they tend to be friends with each other. The reason for this is again that this is, as you will see, it's easy to model this with in terms of statistical physics. Good. So this is one driving mechanism. And then the second driving mechanism is the social balance. So basically, the first one was about the dyadic relations between the two persons and based on the opinion. Now it's solely based on the relations, and it's based on the triangles of opinions. And this is the traditional saying, friend of my friend is my friend, and enemy of my enemy is my friend. And basically, what we observe in these societies is that people tend to prefer these balanced triangles. So this one is balanced where all are friends. This one is unbalanced. This is the friend's enemy, is balanced, and this is the unbalanced triangle. And now the physical interpretation of this is that what we can basically say is that we would like to translate those models into something that we know in statistical physics. And for this, we use the simplest set of models or class of models, which are spin models, because now it's easy to just translate the opinion that is now binary to a spin. So now what we assign is that each person having several opinions is equivalent to, let's say, a particle having several spins. And now the homophily, for example, says that if the spins are similar, then the particles are attracting each other. If the spins are different, then they repel each other. This is basically the idea. And now let's talk about the exact way of how to. Yeah.
The slide before, you had several layers of
Yes.
opinion. And so, for example, the example in the middle, they attract each other on two levels, but in some levels they might.
Yeah. So in the simplest case, and this is what we do very often, is that we say if there are more similar opinions than different, then they attract each other, and vice versa. But you can again, according to the bounded confidence, you can change the level, and maybe there is some threshold that is different, and some threshold where there are neither friends nor enemies, etc. But I will go through that. Good. So basically, now the translation to statistical physics is that so in physics the key quantity or the main quantity is the Hamiltonian of the system, which qualifies the energy of the system. And here, and in statistical physics, of course, the idea is that the system tends to minimize the energy over the time due to the statistical nature or random nature. Effectively, what it does in statistical physics, it minimizes the free energy. Here, we use the similar concept, but now we would like to translate this Hamiltonian into something that would be called social stress. So the main idea is that in physics, the particles tend to, or the system tends to minimize the energy. Here, the society tends to minimize the social stress so that it reaches some equilibrium value. And we will see how it works. So now we define the opinion vector. So what we saw here is that this is the vector of opinions. So we now, for simplicity, write it as a vector. And again, for simplicity, we say it's binary. But in principle, you can generalize it to like any type of interaction. So it can be like finite set, natural numbers, continuous interval, depends on your system. But for simplicity and for starting the analysis, the simplest is to have just two values. And now we also define the relations between the individuals. So this defines the adjacency matrix. And now we can say there are three main classes, which is the two individuals are enemies, they are friends, or they are no relations. And this can be either because there is no contact, or because they don't they are neither they know the two persons know each other, but they are neither friends nor enemies. And we will see that in some situations we also focus on the case where we consider only friends and no enemies, but it depends on the system. Good. So now, if we try to translate the homophily into this social stress Hamiltonian, it will look like this. So it's the sum over all pairs, where these are the opinion vectors. And this dot is basically the scalar product, which is just normalized because you want to have it from -1 to 1. And this effectively measures the similarity between the opinion vectors. So basically it measures the angle between the vectors. And the smaller the angle is, the more similar they are, and then the higher homophily we obtain. So basically this means that this corresponds to Ising model, just that you don't have the spins as scalars, but as vectors. And of course, if you then have the Aij, if it can be both positive and negative, it would correspond to something like a spin glass. But then it depends on your application. But in principle, this is already well studied. This Hamilton is well studied, so we can use many results from statistical physics.
But so you think this you interpreted it as easy model with multiple layers of spin, right?
Basically,
I think there's another interpretation. It's just the scalar product of Sij gives you a quantity that only Wij, and this will be the same like in the Hopi model. So this is
and okay, yeah. Of course, yeah. You can find. I mean, there are many similar models that are similar to using like spin glass, like the Hopfield model of. And I think in economy, in finance, you will find another model that will be similar to this. So yes, definitely, this is not the only interpretation. Good. And then for the social balance, the balance is based solely on relations. So it's independent of opinions. And then if we assume the adjacency matrix to be this, then we can write the social balance Hamiltonian as follows. So it's like the cubic term between all the three vertices of a triangle. Basically, if this is balanced, then this whole thing is positive, is +1. If it's unbalanced, it's -1, and 0 if the triangle is closed. So if one of the things is missing. And this is also has been studied in statistical physics. It's called Baxter-Wu model on the links. So typically the Baxter-Wu model has some. So this would be the spins in this model, but now it's the link. So it's the dual interpretation. Okay, but our aim is to study both of these together. So these phenomena have been studied separately, but the idea is that, and this is what Tuan came with in one of his first papers, is that you combine these two terms, homophily and social balance, and then basically the opinions and relations co-evolve together. Because in the previous models, it was that always either in the homophily only spins were evolving and the connections were constant. Here it was only that the connections, the links were evolving and there were no opinions. So now it's the interplay between these two, where you have the spins and you have the opinions, and these relations co-evolve with each other. This was first introduced in this paper in 2020, and the idea is that basically you can change. So the individual, you as a person, can either to lower your social stress, can either decide to change your opinion or change one of your relations. So basically you say, this person is too different from me, so I will no longer be friend with them, I become enemy with them. Or I say, this person is no longer interesting for me, I can maybe try to rewire my connection. And you can study this by evolving the system, and you see that by subsequent evolutions you can reach the minimal energy level. The problem with this, or maybe I will not talk about the problem first, but about the solution. What is interesting about this model is that this model exhibits a phase transition between balanced and unbalanced state. Balanced state means basically that that you can define an order parameter, which is the relative number of balanced triangles versus unbalanced. So if this f is 1, that means that all of the triangles are balanced. And if it's 0, then all of these are unbalanced. And what to find out is that you observe that there is the phase transition between the balanced and unbalanced triangles, and it depends on the. So first, there is a quantity that is always present in statistical physics, that is the temperature, which here the interpretation is typically that it describes how much the people are willing to change their opinions or their connections. And the second one is the connectivity of a network. So if you have a network, the connectivity network, then basically it depends on whether this, so basically the transition from the fragmented to a polarized society depends on the network degree. Here in this region, why we say it's polarized? Because you typically have several groups that have positive relations within, and then these groups have negative relations between them. It can be that it's only a single one, then it's the what we call party state, that everybody has the same opinion. But this is not very realistic in real society. So more typically what you have is that you have at least 2 large groups that have a similar opinion within the group, but have a completely different opinion between the groups. And this is what causes that you have the group that you have the society that is polarized into 2 or few groups. And here you have fragmented society, because then most of the triangles are unbalanced in the sense that you have many small groups, or even like maybe single persons. And you see it here on this graph, that basically in this region you have many small groups of people that agree with each other, but then there are many negative links, and this causes the whole society to be unbalanced. The problem with the
One question. I have a few questions.
yeah.
One, so also we're trying to get some actual empirical studies in schools in the Netherlands. One thing we show is that, or one thing the data shows is that the effect of like and dislike is hugely more important than opinion. In fact, the opposite. The opinion doesn't matter in these group formations. The other thing that is clear from the observations is that these updates are asynchronous.
Mm-hmm.
So it's not that everyone is updating their opinion and their network at the same time. If you were to put that in the model, it's fairly easy. Would this phase transition disappear? A certain heterogeneity of update frequency.
Okay, that's a good point. I will basically show that we extended these models to a few other extensions where basically we also thought that is somehow unrealistic. And then you see like different behavior. But yeah, so you are right that the effect of whether the likes is not yet here. That will be another aspect. So it's more about real society where an opinion matters.
And the asynchronous question?
Yeah, yeah, true. So that will be actually a good point, because then the problem with the asynchronous update is that you are not sure whether the system follows the detailed balance, in the sense that whether it reaches equilibrium. And then, of course, you might want to use that, but then you will reach the non-equilibrium steady state, and then you will not be able to use the results from the equilibrium statistical physics. So that's mainly the reason. So, of course, the problem, and I will show this, this is with the model, that even here, even when there is the condition of the detailed balance is fulfilled, and even here the system doesn't reach the equilibrium state because of the rough energy landscape. Because what often happens is that you end in the local minimum that is far from optimum, but you cannot, and that's why the asynchronous update would be much more convenient in the sense that then by this synchronous update you cannot escape this local minimum. So this is the main problem. Also, what we think or what we found out is what is unrealistic is that in this model, what an individual takes into account are all of the triadic relations between all of their pairs of friends or enemies, which is not typical in like real society. So you are typically don't know or don't care about whether all of your friends, what are the relations between them, or whether they like each other or not. So by a series of follow-up work that I will be showing now, we tried to somehow see whether we can a little bit relax this social balance condition to make the modeling more realistic. And this was the first extension that we did with Duan, was published in 2021, where we basically assumed that, of course, it's not possible to take into account all of the triadic relations. So what we introduced is a step a little bit towards agent-based modeling, in the sense that we said now there is no global social stress function, but each person have their own local social stress, and in this they care about the homophily between their them and their friends or their neighbors, but then they take only into account a fraction of these triadic relations. So basically we say we care only about, so among all the triadic relations that a person has, they care only about a fraction of the triangles that are most important for them. And then this Q, so basically we can measure the size of this fraction. This Q becomes a parameter, and depending on the fraction, we see that there is again phase transition in the system. Now we have to, of course, update slightly the simulation algorithm, because now it's no longer there is no longer a global Hamiltonian, which means that we cannot use the classical Metropolis-Hastings algorithm that relies on the assumption of detailed balance, which is not fulfilled in general here. So how the way we extended it is that there is a step where you pick a fraction of triangles of an individual eye at random, and this has a certain size that is given, and then we basically do the same update as in Metropolis-Hastings algorithm. The only difference is that we don't use the global Hamiltonian, we use the local one, where we just, in every step, this is different because we take different fraction of triangles. So, and this is the idea behind this is that basically what we try to model is that the agents can become irrational, because what it means that they can effectively increase their social stress. So it's like here. So if I have these three nodes, then basically this agent I can decide that in this triangle it would be better if I change my opinion so that these two links are negative and this triangle becomes balanced. But then I make these two triangles unbalanced, and effectively what I do is that I increase the social stress. But since I was focusing only on this triangle, because, for example, I was like together with these three people, with these two people, and I wasn't together with the person L and M, I didn't care about their opinion so much. or about their relations. So then I basically decided to change this. And globally, it might not be ideal, but it's basically more, we would say, realistic approach to this. And what we showed is that for large enough Q and degree K, the system still reaches the stationary bounds in a fragmented state. So, but for small enough Q, if I stop caring about my friends enough about their relations, then I can get to the unbalanced phase. And then there is again a phase transition. So you see here that it's like quite steep, that there is no, let's say, continuous transition, but it's quite rapid. And so this is for Q, and again for K, the degree, we see the same similar behavior. So if both of the Q and degree are large enough, we end with the same result. And this led us to yet another idea, is that basically in many real-world systems, the tendency to create balanced triangles has been verified. So this is a well-known fact. But it's questionable whether the individuals in the modeling of this are actively seeking for or taking care of whether they are when they change the opinions, whether it changes the social balance or not. And particularly in like social networks where people have like hundreds or thousands of friends, it's not plausible to think that they would care about all the triangles, because then the number of the possible friends of friends relations is so high that nobody can take care about this. So our question was that maybe the social balance can be just an emergent statistical phenomenon that arises as a consequence of these dyadic relations, basically as a consequence of homophily, when correctly written. And so basically what we found out is, so you now have a system where I have a node I, an individual I, and they know the relations to their friends or their enemies, but they don't know these triadic relations. And the key aspect that we found out is that the social balance takes both positive and negative links into account. So basically, it means that I want to have very similar opinions with my friends, but maybe with my enemies, I want to have as different opinion as possible. And we summarize it in like a simple model where we say, so there are like two types of connections. It's the connection between my friends. So again, we take the local social stress, and I say, I want to minimize, so I have to have as similar opinions as possible with my friends. And I want to have as different opinions as possible with my enemies. And then there is the factor alpha, parameter alpha, that tells me about how much I weight between these two. So basically, it's whether I care more about the the opinions with my friends or with my enemies. With alpha equal to 1, we say I care only about my friends. Alpha equal to 0, I say I care only about my enemies. And alpha equal to 0.5, it tells us I care about them in the same way. And what we found out very interestingly, so basically we found out that there is like a phase in this where you can find basically balanced society. So again, this is the parameter f, which is the fraction of balanced triangles that we measured. And there is this region, this yellow region, where we find that the society is basically balanced. And in this region where alpha is high, it's the dominance of this positive relation. So it's the all friendly links. In this region where the alpha is smaller than 1/2, it's caused by this triangles of the form of plus minus minus. So enemy of my enemy is my friend. So basically, we found out that there is a region where the society is balanced, also without explicitly saying that there is any term that is explicitly constraining that the system would tend towards balanced state, but there is indeed a region where it's the case, so it's kind of emerges from the dynamics. And what we also found out is that it's not only about the balanced state, but also we confirmed the statistics of this balanced and unbalanced triangles in the model, and we compared it with an application. So basically, we had access to a data set called Pardus. So it's an online multiplayer game that a former colleague of us created, where we got the data, and you basically in this game you play a game, and you basically earn points in the game by cooperating or fighting against other players. So basically, it allows us to check the links, whether they are positive or negative, and calculate the statistics on the triangles. And what we found out is that there is like an agreement with between the model and the real statistics, that triangle statistics that we observed in the network. So these are the z-scores with respect to the random model, and we found that this corresponds also. I have this now. What we found out is that also the distribution of the positive groups. So basically, what we can do is that you can take the only positive links and calculate the size distribution of the connected components, and then this distribution corresponds to the distribution that you observe in this game. So basically, this is a first, let's say, validation that this model might be useful, and that the social balance could be an emergent phenomenon that is only emerging from dyadic relations. I just want to mention that there is recent paper, again by with Tuan. It's a study done by Meta Galasic and Henrik Olsson, where they try to verify this hypothesis in a real-world experiment, where basically they did an experiment on like people, on 480 participants, and basically they had a methodology how to discriminate or how to recognize whether there are like dyadic or triadic relations. And what they found out is that the people pay attention only to dyadic relationships. So basically, you can imagine it like that. So we have an initial state that is balanced, and then of course, but from the perspective of the homophily, it's maybe not ideal. And what happens is that if the people care about the triadic model, then you will see no change in the behavior. But if there is like the people take care about the dyadic model, so about the dyadic relations, they eventually change their relations, because here, for example, the A changes the opinion because they don't care about whether this link is positive or negative. between B and C, but they can care only about the dynamic relation between A, B, and AC, and then over time you see this change. So basically, they had another, let's say, ingredient that suggests that people might mainly care about the direct relations. Okay, so now in our studies, now we basically mostly work with the assumption that the social balance is mainly emergent phenomenon, especially in large networks, because in large networks or large societies, it's really not possible to think that people care very much about the triadic relations. Whether it's fundamentally true or not, this is of course another question, but at least effectively, it allows us to model the societies only with direct relations and still have the statistics on triangles correct. Now, what we did is that we used it for several applications. So what we calculated as one application is that we calculated the group size distribution, because now what we can focus on is that you, as I said, you can take the groups of positive links, and this is like the group that if you delete the enemic links, will be like a connected component of the system, and you can calculate the group size distribution. And this might be another way of confirming that that this hypothesis is correct, because then if you get the group size distribution that corresponds to the real data, then you will see that this is the correct model that predicts also the statistics well. And in order to do that, we use basically our results from thermodynamics that we did some time ago, where we calculated the extension of statistical physics for structure forming systems. So basically, the idea, now very different, is that we were interested in thermodynamics, where you allow the particles to form molecules. And typically how it's done in statistical physics is that you use the ground chemical ensemble, and you have the particle reservoirs, etc., etc. But then in some cases, especially in cases of small systems, you want to also take into account the canonical ensemble, where you say the number of particles is fixed, and then basically I calculated the exact statistics from that. And the way you use it is that you use the Boltzmann formula. So this is the famous Boltzmann formula. Here, this is the entropy, this is multiplicity, and you calculate the multiplicity for these systems. What you find out is that it's almost the same multiplicity as for regular systems. So you get like a Shannon entropy, but you get a correction. Interestingly enough, what we found out is that already this has been invented or like discovered by Ludwig Boltzmann in 1884, but somehow then has been forgotten. And this paper is not cited at all. But you can use this to basically calculate the group size distribution, because now this Pij is telling you this is the J is the size of this molecule. So basically size of the group. So it tells us what is the size of the group with of size J. And I just say one thing about the calculating the statistical physics, because it seems that this correction might not be so important, and you can work with basically the same framework as in regular statistical physics. There is one small change. So this is the distribution that looks very similar to Boltzmann distribution. The only difference is that here is the parameter alpha. Normally, the alpha is the Lagrange multiplier of normalization that can be somehow related to free energy. The way you calculate the distribution is normally what you do is that you calculate the partition function and then calculate the quantities. Here, basically, what you do is that you have to solve the equation that is now the equation that is a polynomial equation in e to the minus alpha. You have to solve this in order to get the normalization. So you don't calculate the partition function, you kind of solve for partition function. This is the difference.
But what is the meaning of alpha? Is this like chemical potential?
No, in a way. So what we found found out is that you can write. So normally the alpha over beta is minus free energy. Here, alpha over beta is minus free energy minus the number of molecules. And now remember, the number of particles is fixed, but number of molecules is not fixed because if two particles form a molecule, then there is like one molecule less. And particle of size 1 is a special type of molecule. Particle of size 2 is another special type of molecule, etc., etc. So you find that they are kind of similar, but there is like an extra correction to this term. So, but it has the quantity, F minus M, so free energy minus number of molecules plays the role, because then so it's not no longer the free energy is U minus ds. It's no longer the Lagrange Legendre transform of the entropy, but this F minus M is the Legendre transform of entropy. So it plays this role of Legendre transform. Good. So what we did is that, and I don't want to go to the many details, to do is that you use several approximations like the configuration model and mean field approximation. You find that this leads to a set of consistency equation where this is the average magnetization, so the average opinion of a group of size k. And from this, you have a set of coupled self-consistency equation you would have to solve for that. What we did is that we said if the intergroup degree distribution, so is the degree between the groups of different size is 0, then we can solve it analytically. And what we found out is that you get this nice phase diagram where you have the ordered phase and you have the disordered phase. So ordered phase means basically that there is one group of all people that agree with each other. This disordered phase is the group where everybody has random opinion and nobody is friendly with each other. So these are two extremes, but here, in this case, this is the realistic region near the critical, near the phase transition. This is the Monte Carlo simulation. And what we found out is that you can find that the distribution, it's like at this critical point, if you calculate it and compare it again with the Pardus distribution, is similar, has very similar behavior. So it's the group size. So this is all the small groups. This is one large group. So what you observe typically in those systems is that it's kind of due to the percolation that there is one large group that dominates, and there are many small groups of smaller size. And the distribution fits the group size. The theoretical prediction fits the group size distribution in Pardus quite well. So this is another like way of confirming that this model only with the explicit homophily is at least effectively good for describing the social behavior.
Yes, but the question here is, as you mentioned, it's a similar cluster size distribution to percolation, right? So what is the advantage of this approach compared to percolation theory if you don't need to consider the dynamics?
I mean, of course, the problem is that I don't think that in the percolation you would automatically get this group size distribution. I would have to check this, but I think that
exponentially distributed the cluster size for small group in percolation theory, and then the only one single giant component.
Yeah, but the question is whether you would get this from like whether you would get exactly this one without any dynamics. That's the question. That's good.
And you should ask it Shlomo Harley, he know it better than me, but I have the feeling that maybe if you just want to reproduce this
Yeah, but I mean, of course, the idea is that effectively you could describe it with the percolation, but now how to translate it to opinion dynamics? So is it just because of the random connections? Would you get the same?
This may be related to what I said, like with the like and dislike network structure is more important than the underlying opinion dynamic. This may be one reason. But of course, this is a very interesting, how to say, theoretical structure, like the model. I just ask this because of the interpretation, right?
Yeah,
So the interpretation
of course.
can be like generated from the opinion dynamic, but it seems quite like reasonable to assume that if you have the same cluster size distribution in calculation theory, then
Sure.
you can have this alternative.
But then
generating
at least it's like a sign, or like you show that it's not like in contrast to percolation theory, so it's in agreement. So maybe.
But here, the clustering algorithm, how do you determine the cluster? Is it based on the link or based on the opinion?
No, it's based on the link. So in Pardus we don't have the opinion, right?
Oh, I see. Okay, right.
And you say that the fit is quite well. But yeah, you could also argue that the fit is quite bad. Yeah, so is there now a way?
I mean, yes. So
how does this compare to alternative models?
So
same data?
I mean, of course, it's bad, but again, the aim was that what we only used for this fit is two parameters: average connectivity, so not degree distribution, and the temperature. So it's of course bad, but we were able to use two parameters to get this fit. So with like so now and what we effectively considered is that the underlying network is random. So again, this is the connection to the percolation. Maybe if we use the more precise degree distribution, that would
get any other model with only two parameters, they will be worse, you expect in this.
I think so, yeah. I of course haven't tried all of them, but at least this is what we get from this very simple model.
So within this Pardus game, I imagine that within that, even the giant cluster, there are multiple enemies and friends.
Yes, so this is just the friends. This is just we like deleted the enemic, and this is how we get the groups that we say this the group is the connected component in the friendly network. Yes, but then yeah, the reason for this is that then with like the enemy, if you also consider the enemies, then it's much more complicated to solve for this equation, and would be good to do it as a next step, but we want to make sure that we get a simple result.
And there's no rewiring occurring within your model, correct? Okay.
No. So here, I mean, the only rewiring that you get is that you basically say that, and I think I didn't mention it here. The idea also here in what we use is that I mentioned it before. So you say that, so it's not rewiring in the sense that you rewire to another person, but it's the changing of the relation, so that you can change from friendly to enemic relation by saying, if I have more similar opinions with another person, we are friends. If I have more different opinions with them, we are enemies. But there is no real rewiring in the sense that I would basically cut the relation with somebody and then make another relation with somebody else, which would be a great next step, of course.
Do you see how it might affect the model? Because I imagine if somebody finds themselves in a triangle with a lot of social stress, they might just rewire.
We don't know. That would be a great step, but then then with the knowledge we have from the previous model, we will not be probably able to say anything in terms of statistical physics result, or like at least equilibrium physics, because whenever you start rewiring links, it might become really complex, and then you will probably end in some non-equilibrium state. So that might be but yeah, that would be the future, let's say, one of the future projects.
Did you measure the dynamics of the real network?
No,
Is there any fluctuation in group size?
because the problem is that we have only like, so it seems quite a long time, but actually it's not so much data. So we were only able to use this data to get this single distribution over the whole period. So yeah, unfortunately there are not too many players in the.
I wonder, because I guess when new games start, there is some kind of move towards.
Yeah.
That we want to measure, like you start a new game.
Yeah.
Also, you can do a perturbation on it, right?
Yeah. I think, yeah, of course. I think that these are only, I don't remember exactly, but I think these are only the players that played. I mean, either all of the time were like active or like most of the time, because of course there's always this, except many of the players who just start a game and then after 1 hour they never come back. So they pre-filter it so that there are only players who play most of the time, I think, or are active most of the time. Yes, that would be another great point. Okay, and now just to show you what are we working on now. So we are now investigating in this model how, again, the connectivity affects the polarization. So the hypothesis is that with advent of social networks, the average number of connection increased, and the question is whether this model can see, and what we also observed, or what we found out in literature, is that now, of course, this somehow correlates with the increase in the polarization, especially in terms of like political polarization. And we were interested in whether this model can capture these two phenomena. So what now a doctoral student, Markus Hofer, is working on is that he is using the model to calculate what happens is if you increase the connectivity in the network. So you start with the opinion vector, and then you calculate the number of shared opinions between all the pairs. And what you see is that if the connectivity is quite low, then this is the average of opinion distribution. Then this psi, which is the variance of this number of shared opinions, which now this is our measure of the polarization, is low. If we increase this connectivity network, then we see the increase in the polarization, because then this distribution becomes bimodal. So this is what we observe. This is the data from a survey about the political opinions of Democrats and Republicans in the US. So this is from 1999. This is 2014. And what we found in several studies is that basically the polarization in society increased over time. This is just, we try to fit it somehow. And also what we found out from several studies, that the average connectivity, so number of friends, and here it means the number of core friends in these studies, have also increased over the years. And now the hypothesis would be that this increased connectivity could lead to increased polarization in the network. And what we did is that we used this.
Would you choose the variance, right?
Yes.
Check also other measures.
Yeah, we checked. The thing is that the other measures that typically are used is that you can also use the variance of the average opinion, but this is not so precise, because then it can be some configurations where this is low, but still the polarization is high, because what this average opinion can basically show is that some opinions are, so in this case, some of them are 1 and -1, and they are different. But since the average opinion is the same, then you would get low polarization. So this is really that you compare person to person the difference between the opinions, and then you show the variance. So we checked also the others and found out that this one is by far the most accurate, in the sense that, I mean, very often you are not able to measure it because you don't have the data, you don't have these vectors, but we were able to also in the studies to go to the studies and try to and went to the raw data and were able also to estimate this psi. We found out that this is the best measure for the vertical variance. But it works also with other measures.
So the symbol is from data, like in the plot for psi.
Yeah. So this is from, and I don't remember the study, but yes. So basically, you have I think it's the PEW agency that measures. Basically, it asks about and it's only the perception. So it's just how the people feel about the polarization. But we were able to go, because there is like a questionnaire, and they ask about the different questions related to politics, and basically we were able to go and it's the stats are available person by person, so it's like 9,000 or 10,000 people, and we were able to calculate this psi in from the data, and it shows the increase over the time. And they always ask the same question. So it's like one agency that does the same survey over and over each.
Yeah,
you
but
know,
it's
few years.
increased over time is clear, but why it increased in the sigmoidal?
This is just the illustration. It's not like that it would be the sigmoidal function necessarily. It's just that we are anyway missing the data so the data is not available for the latest years. It's just an illustration.
But then the degree also increased in the similar manner with the sigmoidal function.
Yeah, so this is the same fit from the model. So that's like we wanted to somehow model this with the kind of simplest regression model. It doesn't have to be sigmoidal. It's just illustration.
Okay.
But yeah, you are right.
But you can also look at because A is just you could also look at A, the sum of A or the mean A.
The mean A. Yeah, but the mean A is not working because if you have like because this is the number of shared opinions, if this is because it's different, because what we want to distinguish is that in this case the mean A might be also high, but doesn't tell us whether this is like the bimodal distribution or the unimodal.
No, so mean A will tell you that there's lots of disagreement, which
Yes.
is also a form of polarization.
Yes, but
Side gives you the idea that this is clustered.
yes, exactly. That there are like two groups of
Yeah.
because what we don't know in the data is whether like if so we could use it ideally if we knew whether the person would be like voting for Democrats or Republicans, but of course this is not in the data set because they only ask about some questions that are you can then say it's the topics that you can assign whether it's like the opinion is Democratic or Republican, but we don't have the information whether they for whom they would vote or they voted. So that's the reason. So that's basically that you have to then sum up these two distributions, and this is how you then can distinguish whether it's the unimodal or bimodal. That's the reason. Yes, and what we found out is that then is that there is a phase transition in the polarization, So this is the connectivity, and what you find out is that so there is one more parameter that we kind of considered to be useful. Is the gamma is the fraction of so-called instigators. So this is the people who are politically active and that are trying to like push forward the opinion of the party. So they are kind of like their opinion is basically fixed, and they are affecting their neighborhood in order to fix the neighborhood of their opinion. So this like
So they are leader.
either leaders or like because in this case what you get, so in the case where there are no, you get a first order phase transition, so you get this jump. But what we saw in the data is that you get like more continuous phase transition, and then in this case you get the also rapid but continuous phase transition in the polarization and also in the group size. So what you then find out is that the reason for observing the polarization, so again, you measure the group size, the groups, you just look at the networks of positive links, and you measure the group size distribution, you take the maximum group size, and here it's that you have many groups, many small groups, and then there is the jump where you have two large groups and their opinions are really different. So this is the distribution.
So what was K again? I thought K was.
So
K.
so this is the average connectivity.
Okay.
Just a question, maybe this is just a visualization, but it seems that the critical point for the sign and for the group sign are not identical. So
Yeah.
for the green curve,
I would have to check it. I think they should be identical, but it's just the visualization.
but then why for sign it is like smoothly, but for the group sign exhibit some.
No, it's the same. So this is both jumps.
No, for the green one, not for the group.
This is also would be like continuous but very rapid.
Okay.
So this will be also second order. But it can happen that you have like a continuous transition in one order parameter and phase transition in another parameter. Okay, and one last thing I want to show you is that what we've recently done is that we describe an interesting type of phase transition that is both first order and second order transition. So basically it's the abrupt jump, and it's also critical. So it's like critical exponents, and we describe it in our connection, basically again in connection with spin systems. Now they can, like, we use the framework I presented to you before, where we said I have a spin model where the spins can form molecules that are neutral, and we calculated the phase diagram. And the interesting thing is that depending on the degree distribution, you find out that there is the transition between second order and first order transition. And what we found out is that these mixed order transition typically happen if there is some long range interactions in the social systems, in the system. And this is typical for not so much for the natural systems, but it's very typical for social systems where the networks have this small world property that basically you can reach every other node with a very short path. And what we found out also is that the mixed order transition, if you look at the dynamics of it, and if you are at the critical point, then basically what you find out is that there is a plateau. So if you are like slightly above the critical point, what the system does is that it doesn't seem to like go to the other direction, but there's like a long plateau, and then what you observe is sudden unpredicted jump. And the time, the average, so what you see is that both time and the time distribution have some power law. So there is some critical exponent, which basically shows you that predicting the exact tipping point here is almost impossible. And since this is something that is what we observe in social systems, we think that the social systems can be perfect example of this kind of phase transition. You also see it kind of here that if you would take it carefully, what you would see is this is the transition where there is a jump, and probably if you look at the critical exponents here, you would find that this is still critical. So what we think is that this type of phase transitions is very often observed in social systems, and that's why it's very often very hard to predict the jumps in the social systems behavior. But this is just a hypothesis, and this would be like the future work.
For that hypothesis, did you check like critical slowing down?
This is what we are. What is the now the future project of the PhD student that we would like to see, use the real data to verify whether it's the case or not. But the hypothesis is that because of these systems have kind of long-range interactions, it's very likely that they will undergo these mixed order phase transitions, and that's why typically this phenomena like critical slowing down appear, because this is what we observe in these systems, that you have really the traditional methods of recognizing the phase transition fail exactly because of this behavior. So that it be and this is caused by basically that in this region, in this plateau, the system undergoes some microscopic changes in the underlying network that are not visible from the macroscopic figure. So if you look at the system, it looks almost the same, but these microscopic changes change the underlying interaction network, and then there is like a sudden point where it crosses this somehow critical threshold, and then the effective network forces the system to go very quickly to the other state. So this may be the reason that there is a series of microscopic changes in the network that you don't see from like looking at the whole system, but this cascade of changes eventually causes the system to quickly jump to the other phase. So that's the future work. So many of these papers have been done in the collaboration with Stefan Turner, Rudy Hanel, Tuan, and some other students like Simon, Markus Hofer, and now we are starting to collaborate with other members of this Complexity Science Hub, Milton Kalesic and Henrik Olsen, who are psychologists by training, and they are having their own group on studying the social systems, and we would like to connect their results with our theoretical results to see whether they have some real applications in real where we can find it in real data sets. There's also a student who's working on it. These are the references, and I would like to thank you for attention, and if you have any questions, please ask. I think I also have to somehow check the chat, right?
There's no question.
No?
There's no question.
Okay.
So if you go back to the last, the connectivity results.
Mhm.
So what's actually explanation that this happens for you? So because you have two mechanisms, the opinion change and the social balance. So
Yes.
it seems to be that the social balance part of the model causes this because the opinion dynamics is too slow or something to cope. So what's your intuitive explanation why this actually happens?
The social balance basically, yeah, it's just that it emerges just by the fact that the people care both about their friends and their enemies and the opinions of their enemies as well. This is the key aspect, that somehow they have to care, at least to some extent, about what their enemies think, and this is somehow causing the emergence of the social balance. But yeah, I think this is just an effective explanation of this. The question is that whether this is what people really fundamentally think, or how they basically adopt their opinions. And I think that now the useful part is that we at least use it as an effective model. Whether it's like the fundamental description, this is for me still not so clear.
But there could be certain parameters that you now change, and then actually polarization goes down. with
Yes.
Increased scale.
Yes, yes. What is your intuition about this term?
Yeah, I think it's valid point.
Yeah, yeah. I mean, so basically, really, our idea was that it's not plausible that you would that as a person, as an individual, you would care about like if you would have more than 5 friends.
Because my point is in the classical psychological the growth model, all these models, more connectivity means less polarization.
Yes.
It's only the opinion dynamics.
Yes.
You don't have the social balance part, then more connections is less polarization. Now somehow the second part
Yes.
overrules this first.
But yes, because the problem then is that whether like the system can, if you have the opinion dynamics, the system typically reaches to a consensus state, right? Where everybody agrees with each other. But this is very often like not realistic. So these models kind of extend this result to this. So, and this, of course, is the state where you have this full social balance because all the triangles are positive. This is the extension to like the case where you have not a single group of consensus, but 2 or 3 or maybe more groups of consensus. But then, of course, between them, they have to disagree because otherwise you would go back to the other.
My expectation then would be that if you downgrade the social stress part of the balance part in the model somehow, I don't know which parameter that could do, but at some point the effect reverses.
Yes.
And you get the old effect that more connections mean less polarization.
Yes, this is actually what I think you would get, and now correct me. This is if really you care only about the friends, you get less polarization because then you are in this region where all the triangles are positive. So then you are really without this term, you are back to the less polarization. But what we find out that this is like somewhere around the alpha 0.7, I guess, so that you mostly care about the friends, but also somehow care about the enemies. And this is what causes the system to basically reach this other balance state where you see the polarization. And
Interesting.
I think that this is also what is often observed in real systems, not only consensus, but also polarization, right?
I can go.
Just have a question about
Yeah.
the part about the case. Is it just really from 1 to 5? Like
Which one?
from the data, like the part with the parameter size and the case, both from the theory and the experiment. This look like yes, this one. This go up only to 5.
Yes, but this is like Marcus was looking really much to the literature. The problem in the literature is what you mean by the connectivity. So if you say how many friends I have, then everybody would say 50 or 100. But we found out that this is really the number of core friends, because what you need is that you have to listen to those people in order to change your opinion. And this is typically not so many. So it's just the closest friends that you have. And then in the studies, what they found out, especially in these, they found out that it's went from like 2.2 to 4 point something on average. Of course, it's on average, so there can be people that have many more friends, but this is the average value. And this is important because then if you were mixing these between different studies, then you would find very different trends, because it's important that you take the notion of friend in the same way. If you say, is it really the closest friends? Is it just the general friends? Is it everybody whom I like on Facebook? Or can be very different. And then also the numbers can be very different. And people would say, I have because I have 5,000 friends on Facebook, I have 5,000 friends, but this is not what we think, what we mean here.
Any other question?
I was wondering, should it be perhaps that the single relationship contribution should matter less as the degree increases, since a person has like a certain capacity to care about all the relationships around him, that if he has more relationships, they start being diminished.
Oh, would be valid point, but I think in most of the studies we did like only I think the degree was like something like 10 or something, so it's like still quite sparse network. But of course, if we were interested in like really social networks, then even these direct relations would be somehow, yeah, one would not be able to care about their 5,000 friends, and then we would have to shrink it again, probably. But yeah, we didn't look so much to social network. But if this model would, or if somebody would like to apply it for social networks, probably this is a good idea. That again, you take, and that's why we don't take the global Hamiltonian, global social stress, but just the local one that is just the social stress that an individual feels at the moment. So then you would only care about if you, for example, are involved in a discussion on a social network, you would care only about this subset of the people that are involved, maybe, or can be this. So then this local Hamiltonian approach is a good like middle point between the statistical physics and maybe agent-based modeling, because you still have some function that you want to optimize, but this is not a global functional. It's just the local function that can be different for each individual and can be different at different times.
Okay, so other question? If not, then just thanks.
Thank you very much.